So what I'd like to do is to talk a little bit about what we have been doing over the past few years in the area of implementing feedback control and mathematical modeling concept for the design and control of crystallization systems. So what we really do in my group is to try to use process analytical technology not only as a monitoring platform, but mainly to use that information in real time, either for model development and then use the model in real time for process development and optimization, or directly using it for feedback control and the automated design of chemical processes, in this particular case of crystallization systems, by the direct application of the information from the PAT tools. So it's really in the context of what I like to call is quality by control. So I'm going to say that word a few times during my, my presentation. So this is the outline. So I want to talk about our way of controlling crystallization systems by combining information from multiple sensors, a composite sensor array, how we can incorporate this in a kind of process informatics system platform, and how this can be then combined together with a modeling platform to take the measurement, quickly do model identification, and then take the model to improve the measurement and the experimental design in an iterative way. And then the rest are some examples. So I'm potentially ambitious to present all of those. If we won't have time, I can talk about those during the break as well. So one is about how we can use FBRM for quantitative information for directly model, using for model identification and model development, and then how we can get that model to then optimize the crystallization process, then how we can use PBM for again, quantitative information extraction for model development, as well as feedback control, direct feedback control with real-time image analysis. How we can integrate some of these with other inline technologies, potentially where the auto-sampler could be very useful, for example, UPLC for monitoring and controlling crystallization systems in impure media. And then how we can implement some of the concepts that we had developed several years ago for batch crystallization, such as the direct nucleation control, how we can do that in integrated wet mill MSMPR systems, and potentially showing some process intensification approaches via plug flow crystallization systems controlled via FBRM feedback control. First of all, I need to thank to my group from Purdue who contributed to the work that I'm presenting today. Very briefly, crystallization control is very important. There is many technology and economic drivers which suggest that if we can enhance the way in which we control crystalline properties, size distribution, shape, purity, polymorphic form, we can influence both the product effectiveness as well as the efficiency of the downstream processes. So any new methodology which is able to enhance the control of crystal properties can be critical for product functionality and operational efficiency. And all the approaches that I'm going to describe today are based on this concept. So this is the platform that we use, we've been using over the past 15 years, I would say. So we've been working many years ago in integrating information from multiple sensors, because I strongly believe that there is no one silver bullet sensor which can give you all the information related to crystallization monitoring. And it's really, there are a lot of these which provide information which is overlapping, but we also really want to use that information for including additional robustness in the methodologies that we are developing. So this complementary and redundancy in all of these measurements can give us the possibility to apply real-time data reconciliation. So tell, for example, if one of the sensors fail or provide wrong measurement, and also enables us to implement robust control, feedback control strategies, which then can be used as direct design approaches. And what I mean by direct design is that we don't do the typical quality by design approach where you define the space in which your process input can vary, and then run a bunch of experiments, potentially based on a design of experiment method, and then create the quality by design space at the end. we run clever experiments, just run a few sets of experiments, feed that into a feedback control approach, and let the feedback control approach search for the next set of operating condition which will drive the system towards desired set points or target crystal properties, right? So we use imaging sensors, so PBM, a variety of spectroscopy tools, the FBRM, Raman, and more recently we coupled this in cooperation with Waters together with online UPLC to get complete impurity profiles as well during the crystallization to get now really the whole picture of what's happening in a realistic crystallization setup where crystallization occurs in the presence of impurities. So we integrate this together in a software platform which has the possibility to implement a variety of feedback control strategies that we developed in my group over the years, and then drive the crystallization platform, whether that's an EasyMax or a chiller controlled unit, towards achieving desired combination of solid properties. We do this in batch, but also do this in continuous, for continuous crystallization. So we have several platforms in my lab where we have cascade of mixed suspension, mixed product removal crystallizers, so continuous third tank systems, as well as plug flow, oscillatory flow systems, and hopefully I will have some time to show some of these systems. So this is the actual platform that we very recently developed in my lab. We have a fully integrated continuous manufacturing platform, both on a small scale where we are using microfluidic platforms and can combine them as pieces of the puzzles to create a production line of an API and then connect that to a formulation platform where we are using inkjet technology to print that on placebo tablets or in capsules or edible films, either as polymer melt formulations or suspensions or solutions. But we can also do this in a larger scale, so we use continuous Chemtrix-type reactors connected with oscillatory crystallizers, oscillatory flow crystallizers, either as a plug flow system or a dynamic oscillatory, dynamic baffled system, and continuous filtration connected together basically with this formulation platform as well. And all the key idea behind this, because we try to run these continuously, to have a series of process analytical technologies to monitor and control these and maintain the operating conditions at the desired steady state value. As I said, we also work in trying to couple and design these systems by developing mathematical models. And our modeling platform, so previously we've seen a modeling platform mentioned that's routinely being used in industrial applications. There are other, like the G-Crystal, which is specially tailored for crystallization simulations. Our group also released very recently, and you can, if you work in crystallization modeling, you can download this software from this website. We released a population balance model toolbox where if you have kinetic data, you can very quickly do model-based design, model-based simulation of two-dimensional population balance models. So we can really simulate variations and effect of operating conditions on the crystal shape as well as purity. Also is included in the system, so you can go through a very user-friendly graphical user interface and then put in your model parameters and generate very quickly animation simulations and results, and do sensitivity study and optimization and parameter identification for model-based crystallization design. The key idea towards what we are working, that this model-based platform should be integrated directly with the experimental platforms such as the EasyMax and the METTLER suite of measurement devices to provide an integrated system where model-based design can be used for crystallization processes. So this is an example generated by the software output where we do temperature cycling and want to simulate what is the effect of actual constant amplitude temperature cycling on the crystallization. And you can see that it's very interestingly, despite the fact that we are cycling with a constant temperature cycle, the crystallization is not, despite the fact that it's actually following the same trajectory in the phase diagram, we have constant change in the aspect ratio during the crystallization, right? So it's this particular case, aspect ratio increases. I don't talk too much about this, but the fact that this toolbox has a very efficient numerical implementation, the simulation is done on graphical processing units, it's parallelized, it's extremely robust. It enables us to use this in real time, right? So we can solve now very complicated population balance models, takes the information directly coming from the PAT tools, and then do the optimization and calculation of the operating condition by solving even two-dimensional population balance models which describe the shape evolution in real time. And the idea behind this is that with very single or simple experiments, such as taking now FBRM measurements into account, we can do model identification and then model optimization in real time and determine the operating conditions by a single experiment. So the idea behind this is then to try to use FBRM measurement, right? So people have tried to use model identification by offline sample taking and doing master sizer laser diffraction-based measurement, but there is always a question how the model output relates to what we measure. Right? So what we try to simulate and what a particular measurement device gives is never the same, right? So somehow, if we want to get a proper description phenomenologically of what we observe with our measurement device, we have to include in the mathematical model the model of that particular measurement system. So what we did, we derived a model for the FBRM measurement. So we know what FBRM does. There is a laser beam which rotates and then from the backscattered light measured chord length distribution. So not size, it's chord length distribution. And that's definitely not what a population balance model gives unless we incorporate this information and describe that in a mathematical model. So this is what we did by assuming certain shapes, and these can be pre-computed in a database and then taken automatically from the FBRM model module. We compute all the possible chord length, and practically from a single crystal of a particular three-dimensional shape, one would compute an entire chord length distribution. Right? So even if we have a single crystal in our system, in the crystallizer, the FBRM will measure an entire chord length distribution. And if we assume now a population of crystals, the chord length distribution measured by the population of crystals will be a weighted sum of the chord length distributions on the individual components of the particle population. Right? And this is what we actually do here. So we are able to solve a two-dimensional population balance model, do random orientation, two-dimensional projection of those three-dimensional shapes, compute all the chord length distributions, and then based on the crystal size distribution that we simulate, compute the average chord length distribution of the individual components of the size bins in the particle population. With that information, then we can take directly into a model identification approach, so fitting, of course, the concentration variation as well as the chord length distribution now directly into a KP is the set of kinetic parameters that we try to identify. We can identify our kinetic model, so growth rate constant, nucleation constant, dissolution if we include, or any mechanisms that we would include in the population balance model. So this is now a model which will be able to predict what the FBRM measures in the system. So just showing some of the results. So this is a typical cooling system. This is the concentration profile, a relatively good fit. And this is the experimental chord length distribution and the simulated chord length distribution, which describes fairly well the variation. Now, if we have this model, then we can feed this into a real-time optimization and model identification approach, because we have the modeling platform that I described, which is able to simulate very fast, very quickly the population balance model and optimize crystallization conditions such as the cooling profile or temperature, so that we can achieve a desired final chord length distribution at the end of the batch. So showing some of the results in this case. So this is how the whole approach looks like. We start taking some measurement, right? So in the past, we used this measurement to solve a parameter estimation problem in real time now. So we recalculate always the kinetic parameters. If there is any disturbance in the process which would influence, for example, the nucleation rate in our system due to whatever impurity which may have occurred in the system, we take these past measurements and re-estimate the kinetic parameters, taking concentration measurement, chord length distribution measurement, and number of counts measurement into account. And with this new set of kinetic parameters, then at any time step, we'll do an optimization of the temperature profile in the future to make sure that the chord length distribution at the end of the batch will coincide with the desired chord length distribution. So this approach provides a simultaneous model identification. So we learn the process as we are doing the batch, as well as adopt the operating conditions so that under even varying operating conditions, we achieve the desired final target chord length distribution. So this is an outcome that we did. It's an experimental design where basically the model-based optimization was communicating directly in real time with the FBRM measurement, taking that information into account, do the model identification, and recomputing the temperature profile. So we do something, we end up in a single batch with a temperature profile which is relatively as one would expect, right? So this programmed type of cooling where the objective is to minimize nucleation and maximize growth. And we see the chord length evolution and it fits quite well. The desired, this magenta line shows the final, which was the target chord length distribution at the end of the system. So a single batch experiment here provided us the kinetic parameters, which were identified many, many times. Every 3 minutes, actually, we recomputed the kinetic parameters here. And provided an optimal trajectory at the end, even under disturbances which may have occurred during the crystallization system. So single experiment, output is a model with parameters that one can use to optimize the system in offline for other conditions, and it provided the optimal temperature profile for a desired chord length distribution. So these are just some of the PBM images which show that really with this approach, with the same batch time, we were able to achieve much better and larger crystals because the objective was to minimize nucleation than by doing simple linear cooling for the same batch duration in this case. Okay, so let me see then how we can incorporate now PBM more quantitatively in the application of feedback control approaches, and how the same concept that I was mentioning before, that there is always a discrepancy between what we are able to measure and what our population balance model describe can be eliminated. These are some new results where by if you just try to understand what's happening in the case of but this is what's happening anyway. So in ideal case, this would be the aspect ratio that we would measure, right? So this would be the ideal aspect ratio, and this is actually what your population balance model gives you. But in reality, your crystals rotate in a random, you always measure it in a random orientation, and your PBM or imaging tool will measure the two-dimensional projection of this 3D object in whatever orientation it is. And your model has to incorporate this effect. And if you think about it, just like in the case of the FBRM, if you have a single crystal in your vessel and you do the PBM measurement, it will give you an aspect ratio distribution, right? One single crystal, because you will measure it under different random orientation, and your image will be always the two-dimensional projection of that single object. So if you, and because of that, your actual measurement, mean aspect ratio, is going to be under-predicted. So if you consider a crystal which would have 100 micron length and 15 micron width, the mean aspect ratio for that crystal, the aspect ratio of that crystal is somewhere here. But if you compute the aspect ratio distribution, your most likely aspect ratio that you measure is 4.5, right? So we typically under-predicted. And if you have a population of crystals, one would need to take that population into account and calculate the weighted aspect ratios to see what your FBRM, based on the crystal population, what your PBM would provide you as an aspect ratio measurement. Okay, so if we do that, then it actually gives measurement, right? So we have a variation from quite small to 12 aspect ratios with a strong peak somewhere, somewhere here. If we take this now into account and incorporate that into a, we derive now what's happening compared to the real case. So this is the ideal aspect ratio. Don't worry too much about these integrals. My postdoc Botton likes to play with these double and triple integrals. So he took these and derived what's really the difference between the ideal and observed aspect ratio based on the fact that here we have random orientation, and this would be the actual orientation. Again, don't worry about the left-hand side, so we just simulate this now for a two-dimensional population balance model for a crystallization where we have fast and slow cooling. And so this is the evolution that you would get for the two-dimensional population balance model. So we can clearly see that there is a different evolution, so much more nucleation when we have fast cooling versus the lower nucleation when we have slow cooling. And of course, this would lead to variation in the or different aspect ratio distributions as well. And then following that derivation that I just showed before, I'm trying to go through these as these steps basically. So this is the ideal versus the real measured aspect ratio. One can go through these integrals and derive the correlation between the two. And interestingly, we end up with a relatively simple correction factor, which is based on the mean width and length, which can be computed from very simple population balance models, even on the based on moments, not necessarily more complicated entire distributions. And if you apply this correction factor, now we can really make the correlation between a model prediction and what the PBM sensor measures. So if you look at these lines, this is the ideal variation of the aspect ratio in the two cases, so fast and slow cooling. We could analyze what's happening here, so how the cooling rate influences the aspect ratio at the end of the batch. But really the key message here is that by applying this correction factor, so this is what our normal population balance would give us, and this is the ideal, and this is what the PBM sensor measures. So there is this under prediction of aspect ratio, as I mentioned, due to the random orientation. But by applying this correction factor to this modeled aspect ratio, we can get very close the model prediction to the true PBM measurement with within 0.1 aspect ratio unit, right? So in both cases. So this is now allows us to use this measurement as a true measurement tool for real-time shape measurement and the real-time correlation with the output of population balance models. So just showing very quickly how we can integrate this with using our sensor, other systems. So we have the typical system now. We use inline sampling loop to take samples, recycling some of the samples with the UPLC to take impurity measurement. And combining that now, including that and combining with a simple mass balance, we take the measurement from the liquid phase only with the UPLC, but combining with a mass balance, we can calculate the purity in real time. So this is the monitoring of the crystallization system where we had the main component as well as the impurity. This is the measured aspirin concentration, and this is the impurity. We can see that both are decreasing. So this impurity is getting incorporated in the crystal lattice, and the computed crystal purity is declining during the crystallization here. So this is the estimated crystal purity. And we took some solid samples in certain points. So these triangles show the solid samples that we dissolved and then did offline UPLC analysis. And we see that our estimation based on the liquid concentration measurements that we get in real time from the UPLC predicts very well what's happening with the crystal purity during the crystallization. Okay? So this then can be used, this information and measurement, to compute a map how multiple impurities will influence the aspect ratio of a crystal, and then we can incorporate that information into a feed-forward feedback control strategy to directly control shape of crystals by manipulating some additives that we add into the system, which has effect on the growth rates of certain certain phases of the crystal. So this is our continuous crystallization platform, where we take the impurity measurement from the raw material. This provides the impurity concentration. This is the model which describes how aspect ratio changes with respect to the impurity as well as the control additive. So based on this model, and I don't want to talk too much about this, we have detailed mathematical model which helps us to generate this surface. We calculate what is the compensating additive which would be required to achieve a desired aspect ratio. But since this model is never perfect, we need to measure this aspect ratio real time. So this can be obtained from real-time image analysis from the PBM, and then take that information to correct in a feedback way the compensating additive addition to reach the desired aspect ratio. Some results which show what would happen if we have now broadly varying impurity concentration coming into the system. So that would lead to large variation in the crystal aspect ratio and would be very far from what we would desire to have, so a low aspect ratio crystals. And by having this active impurity control approach, how we call it, we can first of all get the aspect ratio to the desired value and have very good consistency in the crystal shape that we are producing. I very quickly go through now how we can use the concept of feedback control in providing better control of crystal size distribution in a continuous integrated wet mill and crystallization system. So we can actually use continuous crystallization or crystal size distribution control in continuous crystallization in 3 different approaches. So the first is just the simple continuous crystallization, right? So the approach here is to take the FBRM measurement, the core length distribution measurement or number of particle measurement, and then manipulate the GHE temperature in the crystallizer to control the number of counts, which is then directly related to the crystal size distribution, right? The idea behind this direct nucleation control is that if we control a smaller number of particles, then those will grow bigger than if we control a larger number of particles, okay? So this is the standard way of doing it. Then we can combine, if we want better control on the size distribution, with a wet mill. And this is the typical way of combining wet mill with crystallization, right? Where you recycle part of the of the system. And if this crystallization run in a continuous mode, then from the number of turnover per residence time, you can control, you have an additional degree of freedom of controlling the crystal size distribution. What we can do, though, is to take the FBRM measurement in the crystallizer and then manipulate the way in which the wet mill generates the number of particles. And since this is a wet mill which is jacketed, we can actually manipulate the temperature profile in the wet mill, and then control the supersaturation and therefore control the nucleation in the wet mill. And that way we separate completely nucleation from what's happening in the crystallizer. And we can take that idea even further and therefore actually use the wet mill as an upstream unit operation, right? So completely differently how traditionally it's being used. We just use it as an upstream unit operation for seed generation. So we take the FBRM measurement now in the crystallizer, manipulate the jacket temperature in the wet mill, and by that we manipulate the supersaturation and control the amount of nucleation happening in the wet mill, okay? So the wet mill in this case is a primary nucleator, a small volume, high shear device where really only nucleation happens, and then therefore we decouple now nucleation from growth, and we have full control on this nucleation. Of course, the shear will also influence the nucleation rate, but also the supersaturation that we can manipulate in the jacket of the crystallizer will influence that. And I just show, so we have a number of papers which describes all of these techniques, and I just show the last one, or I show basically some results with all 3 of these, and I want to show the benefits of using the upstream wet mill, on one hand of decreasing the startup duration in continuous crystallization, because now we completely eliminated the nucleation and we are controlling it in a small volume high shear device, right? So we have a much shorter startup duration, and we are able to produce much better crystal quality, again because we are controlling the nucleation in a small volume device. So there is no large variation in the nucleation rate, which normally occurs in a stir tank in the system, right? So we get better size distribution, shorter startup duration by implementing this feedback control approach here. How it works, just one example. We take the measurement, as I said, in the MSMPR from the FBRM, so number of counts. And if we want to, for example, start producing bigger crystals, we just need to decrease the set point, right? We decrease the number of counts that we maintain in the MSMPR. Automatically, those crystals should, because the residence time is the same, those crystals will grow bigger. And we just change the set point, and the system automatically will find under which temperature we have to operate the wet mill in order to decrease the number of counts and hence increase the crystal size distribution produced in the crystallizer. So what's happening here, we just decrease the operating range. We never give a single set point, we give a range, right? So this is the smaller number of counts. That automatically the direct nucleation control starts increasing the temperature in the wet mill, which will reduce then the number of crystals generated in the wet mill. And once it brought into the new range of target counts in the crystallizer, then the temperature remains constant in the wet mill. Okay, and what temperature value this is automatically found by the feedback control. This is why we call this quality by control. And we can see also from the core length distribution that there is clearly a shift towards bigger particles here. And lastly, I just want to illustrate now how some of these feedback control approaches can be used in designing and integrating several mechanisms in a continuous plug flow system, where we can create particles, spherical particles, to try to avoid problems which would be generated due to fragile or needle-shaped particles. All the processability problems which those type of particles would create can be eliminated because we are processing and formulating them directly in suspension. And after this, just the simple isolation of spherical particles is important, and this can go directly either in capsules or it will flow very well for tableting as well. We also developed this technology now to be able to co-agglomerate these with excipients, so we are able to actually control now the crystallization and co-agglomeration with an excipient in the system. But the key idea is that we use a plug flow crystallization system where in certain zones we control nucleation by antisolvent addition. Then we have a growth zone by either antisolvent addition or cooling profile, spatial profile that we determine, and then start adding binder in the last part of the crystallizer to control the properties of the spherical particles, right? So by controlling where, how much, how long these zones are, we can control the properties of the primary particles, right? How big the constituent crystals are, as well as the micromeretic properties of these spheres. How big the sphere, the porosity, the strength of these spheres coming out from the crystallizer. And we can do this with model-free or model-based approach. So this just illustrates how we implement this in an oscillatory baffled crystallization system. So we have a plunger here and an oscillator, which creates constant amplitude oscillations. So this is a plug flow system with many baffles. So all these are baffles. So this is actually a cascade of 100 MSMPR. So it provides a very good plug flow behavior because those oscillations will create very well mixed cells. And then because we have very good mixing due to the oscillations, we can have a very small mean flow. So we can achieve in a short crystallizer large residence times because heat transfer, mass transfer, and suspension of particles is controlled by the oscillation, not by the flow rate, or the overall flow rate, right? So how this works, I'll just show a very quick video so that you understand the better working of this. And I just want to point out that we have the FBRM here right at the end of the nucleation zone, and this is manipulating the addition of the antisolvent or the temperature in this zone, the nucleation zone, to control the size of the primary particles. At this moment, we only have FBRM, but we are working on incorporating now imaging measurement on the second phase, the growth phase, and the agglomeration phase of the system. So you can see the nice spherical particles, and they are moving, right? So they are moving very slowly because we have a long residence time, but because of the oscillations in the system created by this plunger, these are well suspended, so we don't have issue of settling. But these feedback control approaches then control spatially the size of the nuclei, how big they grow, and then when we start adding, you don't see here exactly, somewhere here, we start adding the binder in the system to create these spherical agglomerates. And all these eventually would be controlled by feedback from imaging tools. Currently, we are having issue to have the right size of imaging tools. So actually, new devices, much more smaller PBM, for example, would be extraordinarily useful in this kind of context. So I just want to finish my talk by summarizing what I was motivating my talk at the beginning, that there are many economic and technology drivers for better control of particulate processes, including crystallization. So just wanted to show some of the academic approaches that we've been working on. And there is a lot of benefits that one can gain by trying to use these tools not only as a monitoring systems which provide better understanding and a better design of crystallization processes, but also as quantitative platforms, quantitative tools for model identification and model-based design, as well as direct feedback control for these systems, whether we apply model-free approaches where we directly take measurements from the crystal properties, or we apply model identification and model-based approach, one can significantly optimize the development time and the performance of these systems, whether we are looking at just single unit operation as a crystallization, or we look at crystallization as an integrated unit operation, like in the last example where it is actually a particle formulation process, right? So we really integrated even the direct product line almost into one unit operation. Okay, so I've finished now here and would be happy to answer any questions you may have.